Hello and welcome to the first video lecture of IB Physics. Today we're going to get into something that isn't actually physics. Instead, we're going to be talking about something that is even more important in some ways to lay the foundation of all sciences that we talk about, just so that we are all communicating using the same language. And that topic that we're going to talk about today is the topic of units. Now, most people don't find units all that interesting, but I am different than that. I think units are one of the most fascinating things because units have this hidden story that most people don't even know about. In our conversation of units, one of the most important things that we start with is the fact that you can have more than one type of observation. And you might remember this back in some of your other science classes. But we categorize observations in two main categories: quantitative and qualitative. And you might remember the difference between these two. Quantitative measurements are measurements that are really looking at how many or how much. It's more of a numerical sort of value. So if I were to say I am 6 feet 2 inches tall, that is a very quantitative measurement defining how tall I am. A qualitative measurement is something that is more of a description. Not everything can be quantitative, or it would be kind of silly to be in a quantitative way. Like if you said something was soft, sure, you could probably quantify that, but that isn't really what anybody is asking for, to say like exactly how soft is that thing that you're talking about. There are plenty of things that are qualitative and are important to be qualitative. There isn't one that's necessarily better than the other. When we do our labs later on this year, it's important that you have a good understanding of both. If you send a car flying down a track and it's bouncing all over the place, that is a qualitative observation that you're making that's important to talk about, even though it's not necessarily this hard quantitative thing that you're reporting. But today, even though these are both important, today we're going to be focusing on this quantitative thing. Our ultimate discussion is going to be, how can you quantify a measurement? If I were to build a table and wanted you to build the same table that I just did, how could I communicate to you how big to make that table? Now, in past eons, we've had units that are very much focused on the human body, things like the cubit, which is the length of a forearm. Now, if I were to say that this table that I just built is two of my forearms tall, that's great if your forearm is exactly the same size as mine, but that's not great, because probably they aren't the same size. So how can we quantify something in a way that we know we're talking about the same thing? And that gets us to systems of units. Now, there are 7 what we call fundamental SI units. SI is an abbreviation here for System International, which is our international system of units. Now, these 7 are going to be really important, and you need to know all of them. It's very likely that you will be asked a question um, about these 7. Now, looking at this list, some of these are actually things that you probably recognize and have seen before. You might recognize the unit of length. Unit of length is the meter. Now, this unit of length here, I have a meter thick, is going to be our standard unit for length. It doesn't mean it's the only unit, but if I'm going to ask you to define something using the SI units, that's what I'm looking for. For mass, our SI unit is actually the kilogram. This is kind of different. It's not the gram. It's not the base unit in the metric system. In this case, we use the kilogram because a gram is just too small to be useful. If I were to report to you my mass in grams, it'd be something like 63,000 grams. So that's not super useful to you. Instead, the kilogram is much more useful. For time, we're going to use seconds. For electric current, we're going to use amperes or amps. You might remember that from experience that you've had with electricity before. In temperature, we're going to define temperature in units of Kelvin. Doesn't mean it's the only unit that we're going to use, but in many of the equations that we're going to need, Kelvin is the unit that we're looking for. For amount of a substance, we're going to talk in units of moles. That's a unit that you might be familiar with from your experiences in chemistry. And luminous intensity is the candela. That is not one that we're going to use in this class. I expect you to be able to report back these top 6. That 7th one is just bonus. Now, units, this list, it's pretty arbitrary. And to give you a sense of that, like this meter stick I have here, it's clearly based on something. Like this isn't the only meter stick in existence, but it has to be defined somewhere. Now, a meter used to be defined as the length that a pendulum would swing half of its maximum distance in 1 second. So if you change the length of a pendulum, it's going to take different amounts of time to swing back and forth. So if you set up a pendulum that goes back and forth at exactly that rate, you now know the length of 1 meter. And I could report to you, if you were in a different country, how to recreate that so that you can then have a meter to use elsewhere. Now, that wasn't a great definition because you had to build something and it didn't seem to be founded in nature. So that was changed to be the length of 1/10 millionth of the distance between the North Pole and the equator, which you can probably guess in 1791 wasn't that accurate of a measurement. But the idea was let's found it in something in nature, something built in the earth. But obviously, that's not a great way to communicate something if you were trying to communicate a length to a different country. So it was redefined as the length of an official brass bar. This is something that existed in the basement in Paris. That brass bar actually changed over time, its length. So it was updated to be a platinum bar, and then updated again to be a platinum iridium alloy bar. But until 1983, our definition of the meter was stuck in this definition of one like physical object that sat in the basement somewhere. In 1983, it was finally defined as the length traveled by light in a vacuum during a tiny fraction of a second. And that was something that we could measure to that level of precision. And it was founded on something in nature that is unchanging. So not a physical object. Now we have a definition for the meter that is based on light, based on something that is governed by the rules of the universe. All of the units have a similar backstory to them. The kilogram was recently redefined because it also used to be a physical object in the basement in a building in Paris. So as we go, all of these units we talk about are really compared to some sort of standard that we are using to measure our consistency. This meter stick is uh, just defined based on other more precise meter sticks used as a standard, and those can trace all the way back to some standard meter stick to ensure their precision and their accuracy. For example, the second is also defined down there based on the vibrations of cesium. Now, these 7 units aren't the only units that we have. Obviously, that wouldn't be enough for us to define all of the things that we're going to have to deal with, especially in this class. So I want to give you a little analogy to figure out where these other units come from. You might know from elementary school art class that there are 3 primary colors that we often talk about: red, yellow, and blue. Now, these 3 primary colors are great, but that isn't enough to create all of the colors just by themselves. Instead, what we do is we mix them together to create secondary colors. So a secondary color, for example, would be like orange, mixing red and yellow together to make a new color. Now, you can create any color by mixing and matching these different primary colors together. And that is going to lead us to where these other units come from. These fundamental SI units, that list of 7, it isn't all of them, but think of them as the primary colors of units. So, for example, 3 of those fundamental units are length, mass, and time. So meters, kilograms, and seconds. We can use those and mix them together in different ways to create new units. Like velocity isn't measured in any of those 1 units in particular, but if you take meters and divide them by seconds, you have a unit for velocity. We call this a derived unit. It's based on these fundamental SI units, but it's not solely one of them. It's a combination. Acceleration, you may remember from dealing with acceleration before, we deal with in meters per second squared. So meters per second is only comprised of these fundamental SI units, meters and seconds, but smashed together to make something new entirely. Force is even more complex. Force, you might remember, we define in newtons, but newtons, I don't see any of these fundamental SI units in them. Turns out Newton is a derived unit that if we break it apart, it's actually just kilograms times meters per second squared. So if I were to ask you later on, once we're using newtons more and more regularly, to define a force using only fundamental SI units, instead of using newtons, you can talk about it in terms of kilograms times meters per second squared. And I know that feels like this academic exercise, so like why would you use that if newtons exists? But it's important to know for all of these derived units, some of them will have names. They're really just representing some other combination that can ultimately be separated out into one of these 7 or multiple of these 7 fundamental SI units. All right, in IB physics, we are going to present units, particularly fractional units, in a slightly different format than you've probably seen. This format, instead of using these fractions like meters over seconds, we're going to present that as meters seconds to the minus 1. We're going to use negative exponents to indicate that something is on the bottom part of a fraction. So seconds to the minus 1 is just the reciprocal of seconds, and is the same thing as saying 1 over seconds. It's just a mathematical property. If we have something on the bottom that is more than just 1 unit, like meters per second squared, all we have to do is just put a negative sign in front of that squared, and it turns into meter seconds to the minus 2. That 9.81 meters per second squared, or 9.81 meters seconds to the minus 2, is exactly the same thing, just different ways to present it. So with that in mind, how would you present this unit of density, grams per cubic centimeter? Very similar to the last one. You would just take grams divided by centimeters cubed, or grams centimeters to the minus 3. And we can do this for all of these other examples as well. And I want to be clear that if you present something using a fractional unit in this class, that is totally fine. I'm showing this to you now because this is the way that these units will be presented to you on the IB exam, and how I will be presenting them to you in different papers or different examples down the road. Just know that they mean the same thing. I don't care, honestly, which one you use. I'm going to use the fractional or the exponents just so that you become more familiar with them, but fractional, also just fine. All right, I want to take a little break from that and then review something that you have probably been exposed to up until now. I hope you have, and it's the metric system. I personally love the metric system. I think it's a great system of measurement, very easy to communicate big numbers or small numbers and convert between them, but not everyone shares my opinion.
All customary measures use man and his labor as the basis of its measurement. What's an acre? It's the amount of land that a yoke of oxen can till in one day. A mile comes from millipasses, or 5,000 paces, 1,000 paces at 5 feet each. A meter is what? It's an abstract division of the globe that isn't even accurate.
So it's completely made up out of nothing.
It's totally made up. And here's something else.
So just as a quick aside, yeah, it is totally made up. We just talked about that, but all units are totally made up.
Now that sounds reasonable. Actually, counting by 10 is pretty good. We have 10 fingers. You can count your money in 10. It's good for abstract calculations. It's not great for measuring things in the real world. There's a reason why our measurement system has 12s, 8s, and 60s. It comes from ancient knowledge, ancient wisdom, from the Romans 12, from the Babylonians 60. Why? Because those numbers divide up evenly into thirds, fourths, halves, and enables common people to make calculations and to measure their lives without complex arithmetic. What's a third of a foot? It's 4 inches. What's a third of a meter? 33.3 something centimeters. It doesn't even add up. You see the problem right there?
I do see the problem, and I've never heard it as eloquently expressed as you just did. I think you give a lot of us heart to keep fighting against the global tyranny of the metric system.
All right, so back to the tyranny of the metric system. In your data booklet, what you should have picked up during the materials pickup time, you will see this presentation of the metric system prefixes. Now, these values are kind of tricky to use, so I want to give you an example or two of how you might use this to convert in the metric system. The value that is given to the number, the value given is the number of decimal places that you're going to move, basically. So here, you'll see these are all raised as powers of 10. So for example, if you're looking at mega here, it's 10 to the 6th. That means you're going to move the decimal place 6 times to convert from mega to meters, or megameters to meters. Now, the biggest thing that I see students do incorrectly is they go the wrong direction. They move it the right number of places, but they move it the wrong way, which makes it very, very wrong. So if I wanted you to convert 900 nanometers into meters, and moving it 9 times, that would either mean you have 900 trillion, 900 billion meters, or 0.000009 meters. Now, you should always just think to yourself common sense. A nanometer, you know, is really, really tiny. Nanoscale is a very, very small scale. So I would expect even 900 nanometers, that should be a pretty small measurement. It would be crazy to say that 900 nanometers is the same thing as 900 billion meters. So we know that the answer, just by using common sense, should be the bottom one, a very, very small number of meters. And what this would look like then is the base unit here is meters. That is not going to have a prefix to it. Nanometers does, and I can find nanometers down here, shows me 10 to the minus 9th, which means I'm going to move 9 times to get to that base unit. And in this case, I'm going to make it smaller because it should be a smaller number of meters than nanometers, and then basically just swoop the decimal place 9 places over to the left. That's also the same thing as saying 900, the number of nanometers, times that value, 10 to the minus 9th. Same thing as swooping the decimal 9 times. So here's some example conversions just to show you how this might work out and some things that are a little bit more common. If I wanted to go grams to kilograms, I find grams, my base unit, to kilograms is going to be moving 10 places. And kilograms is a really big amount of mass versus grams. So I'm going to be moving that 10 places to the left, or 3 places to the left rather, to turn 250 grams into 0.25 kilograms. Likewise, if I find kilograms and micrograms, that mu symbol is a micro. I find that going from micro or kilo to the base unit is 3, and then the base unit to micro is 6. So ultimately, in total, I'm going to be converting 9 places for that decimal, which makes it 3,250,000. And then millimeters to kilometers, a similar thing. Milli to base is 3, base to kilo is 3. So how many kilogram or kilometers should there be in 54 millimeters? Of course, the answer is 6 places, making it much smaller, 0.000054 kilometers or kilometers. A couple other examples that you'll probably see cases of microcoulombs to coulombs, would just be micro to base. Just note here, you don't need to know what that C represents. You can still figure it out based on the fact that there is a prefix and then there isn't a prefix. That means it's a base unit. Megawatts to watts means you move the decimal place 6 times. Of course, there are more prefixes. There's actually lots more. It goes all the way up to yada and all the way down to yocto. So you can have really, really big numbers or really, really small numbers. For us, we're not going to go really any farther than the ones that are in the data booklet. Honestly, the farthest we typically go is nano, and then the biggest we'll typically go is probably mega. So from this lesson, you should be pretty comfortable describing the difference between quantitative and qualitative. Is it something that you measure using numbers or using a general description? You should be able to identify those 7, especially the top 6 fundamental SI units, and tell me if it is or isn't in that list of 6. And then you should be able to use those units to define whether a unit is derived or fundamental. represent fractional units using negative exponents, similar to how you'll see it here in IB physics, and then convert between metric units using prefixes and knowing how many places to move the decimal to make that conversion correctly.